Welcome. This is the Electric Starman. I'm glad you've joined me. This evening, we are stripping away the noise of the day to look closely at a fundamental question that sounds simple on the surface, but unravels into something beautiful and complex when you look through the lens of planetary physics. Tonight, we ask, what is a moon? To the casual observer, a moon is simply a companion in the night sky, a cold rock reflecting the light of a distant star. But to a physicist, to an astronomer, a moon is a dynamic, captive world. It is an object caught in a delicate, eternal tug-of-war between its own momentum and the massive gravity well of its parent planet. We are going to explore the boundaries of these captive worlds. We will travel to the edge of the Hill sphere, the invisible mathematical boundary where a planet's gravitational dominance ends and the vast emptiness of interplanetary space begins. We will look at the Roche Limit, that critical, invisible line where tidal forces become so intense that a moon can no longer hold itself together, tearing apart to become a ring of glittering debris. And we will look at the strange, diverse geology of these bodies. From the hyperactive, volcanic sulfur fields of Io to the silent, frozen, captured asteroids that drift like jagged shards of obsidian around Mars. As always, all the music you hear tonight was composed by me, designed specifically to slow your heart rate, quiet your mind, and give your intellect just enough substance to drift away safely. So, adjust your headphones. Let the weight of the day settle behind you. Let's look into the dark and see what the universe has left in orbit for us. The universe does not leave space empty without a structure. Even in the deep, silent voids between the worlds, there are invisible lines. There are mathematical boundaries carved by gravity that dictate exactly where one realm ends and another begins. When we look at a planet, a massive sphere of iron and silicate rock drifting through the dark, we must look beyond its physical surface. We must look at its sphere of influence. This is known as the Hill sphere. It is a pocket of space, a gravitational harbor, inside which a planet's gravity is strong enough to overcome the immense pulling force of the local star. Imagine a vast, flat plain of dark water. A heavy weight is dropped into the center, creating a deep, sloping depression. That depression is the planet's gravity well. For millions of miles around that weight, the water slopes downward, pulling anything that passes too close into an eternal, circular fall. The outer edge of this slope, where the water levels out, and the gravity of the central sun begins to take over again, is the perimeter of the Hill sphere. Within this perimeter, and only within this perimeter, can a moon exist. It is a sanctuary of stability. It is a quiet zone where a smaller body can find a permanent home, locked in a rhythmic, cyclical dance around its larger companion. If an object drifts outside this boundary, even by a few meters, the fragile balance is broken. The solar gravity well, immense and unyielding, reaches in and pulls the object away, dragging it out into a lonely, independent orbit around the star. But inside the boundary, the planet rules supreme. The scale of a Hill sphere is determined entirely by mass and distance. A massive planet like Jupiter, sitting far from the sun's intense gravitational grip, possesses a vast, sweeping Hill sphere that extends for over 50 million kilometers into the dark. It is an enormous net, cast into the cosmic ocean, capable of holding dozens of satellites in steady, unhurried paths. Conversely, a smaller planet, or a planet that orbits very close to the scorching mass of the sun, has a Hill sphere that is compressed, tight, and fragile. Mercury, sitting in the intense, turbulent gravitational shallows of the inner solar system, has a Hill sphere so narrow that it cannot hold onto a companion. Any rock that attempts to orbit Mercury is quickly torn away by the sun's overwhelming pull. This is why the inner solar system is a lonely place, a landscape of solitary spheres, while the outer solar system is crowded with intricate, multi-tiered systems of captive worlds. When you look into the night sky, you are looking at the architecture of these spheres. Every moon you see is resting safely within a gravitational cradle. The motion of these satellites is slow, deliberate, and entirely predictable. They follow paths carved by the geometry of space-time itself. As a moon travels along the inner edge of the Hill sphere, its orbital velocity must be high, balanced precisely against the intense pulling force of the planet's core. It sweeps through the dark quickly, completing its circuit in hours or days. But out on the distant fringes of the sphere, near the invisible border where the planet's grip begins to falter, the motion becomes incredibly slow, almost meditative. Here, a moon can take months, sometimes years, to complete a single looping journey. The gravity here is thin. The pull is faint, like a memory. The moon drifts through a silent twilight, turning slowly, suspended in a permanent state of near escape, yet always held back by the invisible, ghostly tether of its parent world. As we move inward from the outer edges of the hill sphere, traveling deeper into the dark center of the planet's gravity well, the physics change. The forces grow stronger, more intense, and more dangerous. There is a secondary line, an inner boundary, that represents the absolute limit of physical endurance for a moon. This is the Roche Limit. It is the fracture point. It is the precise distance from a planet's center where the tidal forces exerted by the planet become stronger than the internal gravity holding the moon together. To understand the Roche Limit, one must understand the liquid nature of gravity. Gravity does not pull on a moon as a single uniform point. It pulls on every individual atom, every grain of dust, every boulder, and every hill. Because a moon has a physical width, its near side, the side facing the planet, is always slightly closer to the planet's center of mass than its far side. This tiny difference in distance creates a difference in pulling force. The near side is pulled forward with a fierce, aggressive energy, while the far side experiences a gentler, weaker pull. This difference in force is what we call a tidal gradient. It is a subtle, invisible stretching force. It acts upon the moon like a pair of giant phantom hands, slowly elongating the sphere into an oval, an egg-shaped object pointing directly at the planet's core. If the moon is far away, its own internal gravity, the mutual attraction of its own rocks and iron, is more than enough to resist the stretching. The moon holds its shape. It remains a solid, cohesive world. But as the moon's orbit decays, as it spirals closer and closer, traveling down into the deeper sections of the gravity well, the tidal gradient increases exponentially. The stretching force becomes an immense, grinding pressure. Deep within the bedrock of the moon, faults begin to unzip. Mountain ranges fracture. The internal core of the moon begins to frictionally heat up, groaning under the relentless, rhythmic pulling. When the moon crosses the Roche Limit, the balance flips. The planet's stretching force officially becomes stronger than the moon's internal cohesion. The results are not violent in the way an explosion is violent. Instead, it is a grand, slow motion disassembly. The loose dust and regolith on the near and far faces of the moon simply lift off the surface, floating away into space like smoke. The crust splits open along clean, geological fault lines. The moon is systematically unmade, layer by layer, rock by rock, shredded by the sheer geometry of gravity. Over centuries, the fragments of the broken world spread out along the orbital path, sorting themselves by mass and velocity. The large boulders smash into one another, grinding themselves down into fine, crystalline sand. The ice sheets shatter into billions of reflective shards. What was once a proud, solid moon with mountains and valleys is transformed into a flat, glittering sheet of planetary rings spinning silently in the dark. The origins of these captive worlds are written directly into their orbits and their chemical signatures. When we look across the solar system, we find that moons generally fall into two distinct structural classes based entirely on how they were born. The first class consists of the regular satellites, moons that were formed through the clean, orderly process of co-accretion. These are the native children of the planet, born from the same primordial cloud of gas and dust that formed the primary world billions of years ago. During the early dawn of the solar system, as a young planet gathered mass from the solar nebula, it formed its own localized, spinning disk of debris, a miniature accretion disk. Within this swirling disk, particles of iron, silicate, and water ice bumped into one another, sticking together through electrostatic forces, slowly growing into pebbles, then boulders, and finally into moons. Because they were born from a spinning disk, these regular moons carry a very specific mathematical signature. They possess circular, highly predictable orbits that lie perfectly aligned with the planet's equator. They rotate in the same direction that the planet spins. They are a harmonious extension of the planet itself. When we analyze the light bouncing off these co-accreted moons through spectroscopic instruments, we find that their composition closely mirrors the outer layers of their parent planet. They are made of the same local materials, cooked in the same primordial oven. Their surfaces are often dominated by water ice that glows with a cold, blue-white brilliance under faint sunlight, or silicates that reflect a dull, neutral gray. There is a sense of cosmic order to them. They have been there from the very beginning, spinning in perfect, synchronized harmony for 4.5 billion years. But there is a second class of moons, the irregular satellites. These are the strangers, the wanderers, brought into the planetary family through the chaotic process of gravitational capture. These bodies did not grow up in the planet's local disk, They were independent objects, asteroids from the main belt, or icy comets from the cold, dark fringes of the outer solar system, traveling on their own eccentric paths around the sun. For a capture to occur, a precise alignment of orbital mechanics must take place. As the wandering object passes through the planet's hill sphere, it is moving too fast to be caught naturally. Its kinetic energy would simply carry it right through and out the other side. But if, at that exact moment, the object interacts with another celestial body, or passes through a thick cloud of gas surrounding the young planet, it loses energy. Friction slows it down. A fraction of its velocity is bled off into the dark. Suddenly, its kinetic energy falls below the gravitational potential of the planet. The trap snaps shut. The object is caught. Because they were captured arbitrarily, these moons have highly irregular paths. Their orbits are often wild, elongated ellipses, tilted at extreme angles relative to the planet's equator. Many of them are retrograde, meaning they orbit backward, moving against the direction of the planet's spin. Their surfaces are dark, covered in carbon-rich molecules that absorb light, reflecting only a faint, dull ochre or charcoal hue, revealing their ancient, deep space origins. We have spoken of the quiet borders of the hill sphere and the shattering violence of the Roche Limit. But there is an intermediate zone. There is a state of existence where a moon is pushed to the very edge of destruction, yet manages to hold itself together. In these intermediate zones, gravity does not merely orbit, it tortures. It works upon the moon like a mechanical engine, driving a process we call tidal flexing. To understand this engine, we must look to the inner orbits of Jupiter, a gas giant so massive it acts as a secondary sun, anchoring its own miniature solar system. Here we find the moon Io. To the optical eye, Io is a bruised, chaotic sphere, lacking the calm, cratered stillness of our own moon. It is a world constantly remaking itself, trapped in a mathematical paradox known as Laplace resonance. Io does not orbit Jupiter alone. It is locked in a rhythmic, gravitational dance with its outer neighbors, Europa and Ganymede. For every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This is not a coincidence. It is the stabilizing geometry of the cosmos. But this perfect timing comes at a terrible physical cost. Every time Io passes between Jupiter and Europa, it experiences a simultaneous, opposing gravitational pull. Jupiter pulls inward with a massive, crushing weight. Europa pulls outward with a sharp, transient tug. Because of this constant, opposing tug-of-war, Io's orbit cannot settle into a perfect, peaceful circle. It is forced into an ellipse, and because its orbit is elliptical, its distance from Jupiter changes every single day. As Io swings closer to the massive planet, the gravitational tide rises exponentially. But this is not a tide of water. Io possesses no oceans. This is a tide of solid rock. The gravitational gradient is so steep and the pulling force so immense that the physical, solid bedrock of the moon bulges outward. The ground beneath your feet would rise by more than 100 meters, lifting up toward the black sky, only to slowly subside as the moon swings further away on its elliptical path. This rising and falling happens continuously, endlessly, compressing and expanding the moon's silicate mantle. Imagine taking a thick piece of wire and bending it rapidly back and forth. The point of the bend becomes hot, driven by internal friction. Now, scale that wire up to the size of a planetary body. The friction generated by billions of tons of rock grinding against itself, expanding and compressing in the vacuum, generates a staggering amount of tidal dissipation. The interior of Io is literally melted by gravity. The rock liquefies into vast, subsurface oceans of churning silicate magma. Pressure builds until the crust fractures, and the heat must escape. This makes Io the most volcanically active body in the solar system. The eruptions here are not like terrestrial volcanoes. Without a thick atmosphere to suppress the blast, the magma and trapped gases explode violently upward, creating umbrella-shaped plumes of sulfur dioxide that reach 500 kilometers into the black void of space, freezing instantly in the cold and falling back as toxic snow. When we look at the spectroscopic light reflected from Io's surface, we do not see the neutral grays of ancient stone. We see the vivid, chemical fingerprints of sulfur allotropes. Sulfur is a highly reactive element that changes color depending on its temperature and molecular chain length. Where the magma first breaches the surface, at over 1,000 degrees Celsius, the sulfur is black or a deep, glowing red. As it spreads across the plains and begins to rapidly cool, the molecular chains shorten, and the color shifts to a bruised, violent orange. Finally, as it freezes entirely in the ambient cold, it settles into a sickly, pale yellow. The entire surface of the moon is a frozen, toxic painting, colored by the relentless friction of gravity. If the tidal flexing of Io produces fire, the same mechanical engine operating in the outer darkness of the Saturnian system produces something entirely different. It produces an ocean. Here, drifting gracefully within the golden, sprawling rings of Saturn, we find Enceladus. It is a tiny moon, barely 500 kilometers across. By all traditional laws of planetary cooling, an object this small should have frozen solid billions of years ago. It should be a dead, silent sphere of solid ice. But Enceladus is not dead. It is blindingly, perfectly white. It possesses an albedo, a measure of surface reflectivity of almost 1.0, meaning it reflects nearly 100% of the sunlight that strikes it. It is the brightest object in the solar system, coated in a layer of pristine, undisturbed, microscopic snow. At the south pole of this tiny world, deep fractures scar the icy crust. These are the tiger stripes, 4 parallel linear depressions, each over 100 kilometers long. They are tectonic wounds, and like Io, Enceladus is caught in an orbital resonance, this time with the larger moon Dione. The resulting tidal flexing does not melt rock, but it is more than enough to melt water ice. Beneath the frozen, brilliant crust of Enceladus lies a global, subsurface ocean of liquid salt water. It is a dark, lightless sea, completely sealed off from the vacuum of space by miles of hardened ice. But at the South Pole, where the ice shell is thinnest, the tidal flexing forces the tiger stripes to open and close. The walls of these massive canyons slide against one another, generating localized frictional heat, keeping the deep fissures from freezing shut. Through these open fissures, the pressurized liquid water of the interior ocean is suddenly exposed to the hard vacuum of space. In a vacuum, there is no atmospheric pressure to hold water molecules together. The water boils instantly, expanding with explosive force. This is the process of cryovolcanism. Massive geysers of water vapor, organic compounds, and tiny ice crystals blast out of the tiger stripes at supersonic speeds, creating towering, ghostly plumes that reach hundreds of miles into the dark. Most of this water falls back to the surface, painting the moon in that fresh, blindingly white snow. But some of the material escapes the moon's weak gravity entirely, feeding directly into Saturn's E-ring. Enceladus is literally bleeding its own ocean into space, creating a massive, diffuse torus of microscopic ice that circles the giant planet. When our instruments pass through these plumes, tasting the chemical makeup of the ejected mist, they detect something profound. They detect the spectroscopic signatures of salt, of ammonia, and of complex organic macromolecules. Most importantly, they detect microscopic particles of silica or silicon dioxide. These silica particles can only form under very specific, highly energetic conditions. They are the undeniable evidence of hydrothermal vents. Deep beneath the ice, at the very bottom of the dark alien sea, the liquid water must be interacting with a hot, rocky core. The water percolates through the porous rock, heating up, dissolving minerals, and shooting back into the ocean through alkaline vents. It is a process called serpentinization. It is exactly the same chemical process that occurs at the bottom of Earth's oceans. The very environments where we believe biological life first began in the dark. Enceladus is a tiny freezing moon, but deep within its icy voids, it harbors the warm, chemical engine of creation. We move now to the largest of Saturn's attendants. We move to a world that defies the very definition of what a natural satellite should be. A moon is supposed to be an airless, silent rock, stripped of gases by the solar wind or the overbearing gravity of its parent planet. But Titan is an anomaly. It is the only moon in our solar system wrapped in a dense, opaque and heavy atmosphere. If you were to stand on the surface of Titan, you would not need a pressurized spacesuit. The atmospheric pressure here is 1.5 times that of Earth. It is a heavy, thick, smothering blanket of gas pressing down on the icy bedrock. But you could not breathe it, and you could not see the stars. The sky of Titan is not the translucent, scattering blue of our homeworld. It is a thick, impenetrable, glowing orange. This is a smog of complex carbon-rich molecules formed through a relentless, slow-motion chemical reaction operating in the upper atmosphere. The air here is composed of roughly 95% nitrogen and 5% methane. When high-energy ultraviolet photons from the distant sun strike the very top layers of Titan's atmosphere, they possess enough sheer kinetic energy to shatter the molecular bonds of the methane gas. The methane molecule, one carbon atom surrounded by 4 hydrogen atoms, is violently decoupled. The light, energetic hydrogen atoms immediately boil off into the vacuum of space, lost forever to the solar wind, but the heavier carbon atoms remain. These lonely carbon atoms drift downward, aggressively seeking new bonds. They latch onto nitrogen, onto other carbons, forming long, complex organic polymers. These heavy, carbon-rich chains are called tholins. It is these tholins that give Titan its distinctive amber hue. When we look at Titan through a spectroscope, the tholins absorb almost all of the short wavelength blue and ultraviolet light. They only allow the long wavelength red and infrared photons to scatter and escape, creating a permanent, glowing photochemical twilight. This heavy organic smog slowly clumps together, growing heavier and heavier until it begins to fall. It rains down through the dense nitrogen air, coating the surface of the moon in a sticky, dark, organic sand. The dunes of Titan, stretching for thousands of kilometers near the equator, are not made of silicate rock. They are made of solid, pulverized plastic, drifting slowly in the cold, sluggish winds. But the most mesmerizing feature of Titan lies near its northern pole. Here, the temperature rests at a stable 94 Kelvin, or minus 290 degrees Fahrenheit. At this specific temperature, under this specific atmospheric pressure, water is as hard as granite. It forms the actual bedrock of the world. But methane and its chemical cousin ethane reach their triple point. They become liquid. Titan has a complete, functioning hydrological cycle, but the fluid is not water. Deep, dark clouds of methane gather in the orange sky. They release torrential, slow-motion downpours of liquid natural gas. These alien rains carve deep, meandering river valleys into the water ice mountains, flowing down into vast, silent bodies of liquid like Kraken Mare. These are true extraterrestrial lakes. They are mirror smooth, disturbed only by gentle, sluggish waves, operating in the eternal, freezing twilight. It is a complete, functioning world, echoing our own, but built from an entirely different, colder chemistry. We must now leave the grand, complex systems of the outer gas giants and travel inward toward the terrestrial worlds. We move into the territory of irregular satellites. We move to the captured shards. Orbiting closely around the dusty, rust-red sphere of Mars, we find two of the darkest, most desolate objects in our immediate cosmic neighborhood: Phobos and Deimos. They do not share the perfect spherical symmetry of the co-accreted moons. They are jagged, deeply cratered, potato-shaped fragments of ancient stone. They are travelers from the deep dark, caught long ago in the Martian gravity well. When we bounce radar off these bodies and analyze the faint, returning light, we find that they are almost entirely devoid of reflectivity. They have an albedo of just 0.07. They reflect only 7% of the light that touches them. They are as dark as coal or fresh soot. This darkness is the spectroscopic signature of carbonaceous chondrites. These are some of the most primitive, unaltered rocks in the universe. They were formed in the very first freezing epochs of the solar system, out past the frost line. Their deep, charcoal black color comes from heavily oxidized iron and a high concentration of trapped, ancient organic compounds. They absorb the light of the sun, hiding silently against the black backdrop of space. Because they are so small, they possess almost zero internal gravity. If you were to stand on the surface of Deimos, a gentle leap would carry you high into the vacuum, and a strong, running jump would grant you escape velocity entirely, sending you drifting away into the dark. But it is the orbit of the inner moon, Phobos, that tells the most tragic story. Phobos orbits closer to its parent planet than any other moon in the solar system. It skims just 6,000 kilometers above the Martian surface. It is so close and orbits so fast that it outpaces the rotation of Mars itself. To an observer standing on the red sands of the Martian equator, Phobos would appear to rise in the west, streak across the sky in a matter of hours, and set in the east. But this blistering speed is a symptom of decay. Because Phobos orbits faster than Mars rotates, the tidal mechanics are inverted. The tidal bulge that Phobos raises on the Martian surface constantly lags slightly behind the Moon. This lag creates a very subtle, but very persistent, backward gravitational pull. It acts as an orbital brake. Through the relentless process of tidal deceleration, Phobos is losing its orbital kinetic energy. Its orbit is decaying. It is spiraling inward, dropping closer to the red planet at a rate of roughly 2 meters every 100 years. It is a slow, agonizing fall, but the math is absolute. In roughly 50 million years, Phobos will finally reach its absolute boundary. It will cross the Roche Limit. The immense tidal gravity of Mars will overcome the weak, brittle internal cohesion of the carbonaceous stone. Deep fault lines will spiderweb across the dark craters. The rock will groan, and then silently, it will shatter. The ancient, captured asteroid will be torn into billions of pieces, and Mars, for a brief epoch of cosmic time, will wear a dark, glittering ring of shattered moon dust. We now return home. The Earth-Moon system is often analyzed through the lens of history, culture, and mythology. But when viewed through pure astrophysics, it reveals itself as a profound anomaly. Most moons in the solar system are insignificant particles, tiny specks orbiting immense planetary masses. Our moon is different. It is the largest satellite in the solar system relative to its primary world. This vast disparity in mass means that Earth does not merely dictate the moon's motion. Instead, both bodies influence one another in a profound mathematical system. We do not orbit a central point. We rotate around a shared center of mass called the barycenter. For the Earth and Moon, this barycenter is not at the center of the Earth. It is an invisible pivot point located roughly 1,700 kilometers beneath the Earth's surface within the solid mantle. As the Moon completes its circuit, the entire Earth responds, wobbling slightly in its orbit as it revolves around this shared focal point. This dynamic creates a powerful, alternating tidal force that moves across our oceans twice a day. It is a slow, rhythmic sloshing of water, driven not by wind, but by the relentless geometry of the Moon's proximity. But the most important role the Moon plays is not geological, it is stabilizing. Over billions of years, the strong gravitational grip of the Moon has acted like a dynamic flywheel. It has dampened the unpredictable, chaotic forces exerted by the rest of the solar system, specifically the gravitational pull of Jupiter. Without this massive companion, Earth's axial tilt, the reliable 23.4-degree angle that grants us our reliable seasons, would not be stable. Left to drift, Earth's axis would begin to precess violently. It would wobble wildly over centuries, potentially tipping the planet entirely on its side for epochs, pointing one pole directly at the sun, while plunging the other into an ice age twilight. This chaotic climate would erase agricultural stability and stifle the continuous evolution of complex life. The Moon is not merely a companion. It is our environmental anchor. It has locked Earth into a steady, reliable rhythm, allowing complexity to emerge over eons of rhythmic, mathematical stability. As our tools for observing the dark have grown more powerful, we have learned that the definition of a moon does not only apply to grand spheres or even jagged, captured asteroids. We have begun to find moons that are closer to particles of frozen light or architectural anomalies than solid worlds. We call these the minor satellites, or the ghost moons. These are tiny bodies, often only a few kilometers across, operating on the absolute margins of stability, deep within the complex geometric ring systems of the gas giants. They do not merely orbit in the dark, they define, preserve, and manipulate the very structure of the rings themselves We call them shepherd moons. Visualize looking across a perfectly flat, geometric plane of Saturn's ring ice. A gap is flawlessly swept clean by a tiny, almost invisible shepherd moon, perhaps Prometheus or Pandora. If a particle within the F ring attempts to drift outward, its slightly slower velocity gives it a delicate inward tug, pulling it back into line. If a particle attempts to drift inward, the internal shepherd speeds it up, pushing it outward. These tiny shards, perhaps just 10 kilometers across, use their microscopic gravity wells to sweep the edges of the ring sharp and clean, maintaining its structured boundary against the chaotic spread of cosmic dust. Even stranger are the Trojan moons, sometimes called co-orbital satellites. They prove that in the precise logic of gravity, even a phantom can find a home. These moons exploit invisible, mathematical islands of stability known as Lagrangian points. Islands of mathematical perfection where the outward centrifugal force and the inward pull of massive gravity wells perfectly cancel one another out. For instance, Saturn's massive moon Tethys is not alone. As it orbits the gas giant, it is not moving through an empty path. Precisely 60 degrees ahead of it and 60 degrees behind it along the exact same orbital circle are two tiny, irregular ghost moons, Telesto and Calypso. These Lagrangian points function as potential wells, like marbles sitting at the bottom of a bowl, trapped in an eternal stable configuration. They are the dust gatherers of the orbital plane, accumulating cosmic debris for billions of years, creating faint, ghost-like echoes of the larger moons they companion, visible only to our most sensitive scientific instruments. We have now seen how moons are formed, how they act, how they are torn apart, and how they define their systems. But nothing in the cosmos is truly static. When we observe an orbit, we are not looking at a permanent arrangement. We are looking at a single snapshot of a slow, unyielding process called orbital evolution. The same physics that lock a moon into companionship also dictate that this companionship must eventually end. The force driving this patient unraveling is tidal dissipation, the very process that powers the volcanoes of Io and the oceans of Enceladus. When a moon generates a tidal bulge on its parent planet, that bulge creates internal friction. It takes energy to stretch a solid world or a gaseous atmosphere. That energy must come from somewhere. It comes from the orbital momentum of the moon. We have already explored the tragic fate of Phobos. Because it orbits so close and so fast, faster than Mars rotates, it experiences tidal deceleration. It is spiraling inward, dropping closer to the red planet, doomed to eventual unmaking. But in systems where the planet rotates faster than the moon orbits, mechanics flip. The tidal bulge that our moon pulls on Earth's oceans constantly lags slightly behind the moon's actual orbital path. This lag creates a very subtle, persistent forward tug, accelerating the moon. This energy boost pushes the moon further away. Every single year, our moon drifts 3.8 centimeters further out into the deep dark. It is a microscopic, irrelevant change on a human timescale, but over cosmic time, it is definitive. The moon is leaving us. This final, patient drift is the ultimate quiet end of companionship. A once massive satellite will physically spiral inward to its physical unmaking, or patiently unravel and drift outward to the absolute boundary of its planet's hill sphere. In billions of years, the far-off future Earth will be a solitary sphere, with a distant sun illuminating an empty night sky. The gravity wells that once held captive worlds will be empty. The universe, through the relentless and patient geometry of tidal forces, eventually resets its systems. Everything must find its final, quiet level of solitude, spinning alone in the immense and unyielding dark.